Hi there, I'm Jeff Utter, and that's my daughter Olive behind me there. She'll be back a little bit later in the talk. Today we're going to talk about Recon. But first, let me introduce myself. I work at Bleacher Report. I work largely on the social and community parts of our application. At Bleacher Report, we deal with like a certain scale of traffic, particularly around breaking news, where we get these significant spikes, sometimes up to 20 times, usually more around like 4 to 5 times. And these spikes happen over just the span of a couple minutes. And therefore, they're really difficult to reproduce when errors happen. So sometimes, and this happens fairly frequently with our work, we have to find these bugs and catch them in production when they're happening real time. So that brings me to Recon. This is a tool that I've used a lot in production to track down these kind of issues that you just can't reproduce locally. This talk is called Recon Revisited. The reason it's revisited is because last year at ElixirConf 2020, I gave a talk called Debugging Live Systems on the Beam. And in that talk, we covered a lot of the lower level built-in functionality in the Beam for doing tracing. And that includes the debug module and the Erlang trace function. And the punchline of that talk was sort of like, we have these built-ins, but you probably want to be using Recon for these. So today we're going to dive a little bit deeper into Recon. A brief outline of the talk, we're going to cover what Recon is, why you'd want to use it. We're going to cover some basic tracing with Recon, troubleshooting a real-world problem that I had using Recon. We're going to touch on windowed metrics and some additional features that come with Recon. So what is Recon? It's a library written by Fred Hebert. It wraps Erlang trace and other built-in process introspection tools, but it has a focus on being production safe. A lot of the low-level tools, they'll allow you to kind of shoot yourself in the foot if used incorrectly. And Recon tries to force you down the happy path of using these things in a safe way. So why don't we use the built-in tools? We have the debug module and the Erlang trace function. Why don't we use them? First off, I think the interfaces are somewhat confusing, particularly the debug module. You have calls that look like this. You have debug.tpl, and then this 3-item tuple, which you'll see that 3-item tuple in Recon as well. But then you also see this atom at the end, which is X, and it's really hard to find what that even means in the documentation. I think it's a shortcut for a few other options. That module has these other functions to debug.tp, .tpl, TPE, CTP. The only one of those I can tell you offhand what I think it means is TP is for trace process. But it's definitely something where if you're using that, you probably need to have the documentation up for reference, whereas I find that Recon is a lot more intuitive, and after you get used to it a little bit, you can use it pretty freely. And they're also not production safe by default. With the trace function, you have to provide it with a trace process that receives all the traces. And if you're not careful, you can run yourself into some problems. The process could end up running in the background forever, tracing your system for eternity or until it gets shut down. And you could dump unbounded amounts of information to your console. So there's some issues there that you really need to handle with consideration, whereas Recon does that for you. So Recon, why do we want to use Recon? Like I said, it's production safe. The tracer links to the shell that you're in, the group leader, and the formatter links to the tracer. And when you, so if your shell shuts down, like if you get disconnected or you just quit out of the shell, if there's a trace running, Recon gracefully shuts everything down and stops tracing. Another nice thing that Recon does is it forces you to choose a number of traces when you're tracing. So you can say, I want 1,000 traces, and it'll trace 1,000 traces and then shut itself down. With the other methods of tracing that are built in, this doesn't happen. You have to manually shut down the tracer when you think you're done. So you could easily forget that. If you get disconnected, you have to find the trace process and kill it. Recon makes you set that limit up front. Also, the code for Recon is fairly well organized and readable, even if you're not familiar with reading Erlang code. I think this is important because we're talking about how it's production safe. So diving into that code a little bit, you can find some good patterns that can help even outside of debugging and tracing. So the first thing we're going to look at is doing some simple call tracing. So we're going to use Recon trace calls. And for me, this is kind of the gateway drug into Recon. Recon has a lot of other tools in it, but this is the one that I find the most useful. It's what kind of I gravitated to Recon for, and I still use it to this day. So let's look at the syntax for it. You call Recon trace calls, and you give it this 3-element tuple that we mentioned before. The first element is a module. The second element is the function that you want to trace. And then the third element can change. You can either pass it the number of arguments that the function takes, or the atom return trace, a PID, or a match spec. And we'll dive into each of those later. The next argument you pass it is the number of calls, like I said before. And lastly, you can pass it some options. Now, when you're using Recon trace, you need to be connected to a system that you're tracing on. You can trace things locally, but where it's really interesting is when you're tracing on production systems, right? And that requires getting access to those systems and getting a remote shell, which we're not going to cover today because that can vary so differently depending on how you deploy your code. So just note that that's step one. I do mention an article at the end of the talk that kind of covers different ways that you can connect to a remote shell. So that's probably a good starting point if you don't already know how to do that in your setup. So let's look at a simple Recon trace. So we're going to do Recon trace calls. We have this module called comment that has a create function. It's for, guess what? Creating comments. Really simple. We're going to tell it that the function has an arity of 1 and we want to collect 1 trace. So when we call it the function like this in our terminal, we pass comment.create, we pass it this map that has a user ID for who created the comment and then the body of the comment. Real simple. And it just returns comment created. Well, once we press enter and it returns that, it then returns to our console the trace, which consists of a timestamp, the PID for the process that call happened in, and then the module and function and arguments that it was called with. Now, these are formatted in Erlang term format. So they might look a little different if you're used to looking at Elixir code, but it's still, I think you can probably still decipher what this is, right? It's a map that has a user ID, which is a string, and a body, which is also a string. Now, since we didn't use return trace, that's all we get with the exception of this one message here. It then says Recon tracer rate limit tripped. And what that means is we got that one call and Recon's now shut down. It's no longer running. So now let's look at return trace. It looks very similar, but instead of telling it the arity of the function that we want to trace, we just give it this atom return trace. And a thing to note here is you'll notice that for the number of traces that I want to collect, I put 2. I actually want 1, but the way that Recon works under the hood is the trace process that receives all the tracers and displays them to your terminal just counts how many times it's been called before shutting it down. And when you have return trace, it ends up getting 2 calls, one for the call and one for the result. So let's say you want to collect 10 traces of both the call and the result, you would put 20 here. You have to double the number. So we call our module and function the same way, and we get the same trace back, but then we also get the return of that trace, again, with a timestamp and the PID of the process and everything, and then what that function actually returned, and Recon tracer rate limit tripped like we expect. Now, there's a pro tip here, which I have to admit I only learned a couple months ago. One of the options you can pass as the third argument is scope local. And if you're a coworker of mine, you might want to plug your ears for the next 30 seconds as I admit to something. Before I learned about this option, I may have, on an occasion or two, when I needed to debug a private function, copy and pasted the code into my editor, find and replace all the def p's with def, and pasted it back into my console to replace the running code so I could trace it. I'm not proud of that, but sometimes you got to do what you got to do. So, but now, obviously, this is the safer way to go about it. You can pass this option scope local, and you can trace private functions as well. So now I'd like to talk about match specs. This is perhaps one of the most powerful parts of Recon. It's based on the underlying Erlang trace function. First, we're going to look at a match spec and see how it works, and then we'll break down what it actually is. So we call recon trace calls, we pass it the module and the function, and then we pass it this data structure. That's kind of a beast to look at. And like I said, we'll break it down in a second. Now when we call comment.create and we pass it this comment with a user ID of 000, it returns like it would, and we don't get a trace because that those arguments that we pass to comment.create don't match our match spec. And then when we call it with another comment that does match, we get our traces like we expect. This can be super helpful in debugging production systems where functions are being called a ton, right? Maybe you know that there's some issue that's only affecting certain users, and the function gets called with the user ID and as one of the arguments. You could write a match spec and use that so you only see traces that are relevant to what you're looking for. Or another example is maybe you have a module that calls Redis or something, and you know you only have issues with the return of one command. And fortunately, Redis takes like a list of strings for the arguments. So you could write a match spec that matched on that, and you'd only see the calls and the responses from those calls for ones that match your match spec. Now let's look at this thing. This is a fairly simple match spec. You're only matching on a function with one argument that has a map in it and sort of one condition on that. So I'm not even going to really dig into the syntax of this. There's pages and pages on it in the Erlang documentation. But needless to say, even for a simple one, it's fairly complicated and they're kind of difficult to read and write. And I wouldn't want to be trying to write one of these out on the production system while I'm trying to, in the heat of the moment of debugging something important. So fortunately, there's a solution for this. There's another library called EX2MS, written by Eric Meadows Johnson. And the nice thing about match specs in general and this library is the match spec is just a data structure. You don't have to compose it or create it on the system that you're debugging. So what you can do is, especially on Elixir 112, you can use mix install. You can fire up a local IEX instance and install EX2MS and compose your match spec locally, and then just copy it to the remote machine. So if we run mix install, we tell it we want EX2MS, we don't care about the version. It does what it's supposed to do, and then we can use it. So to use EX2MS, just briefly, you import it, and it imports a macro called fun. And it sort of looks like you're defining a function. You have fun, do, and then a tuple that contains the arguments for the function, and then guards. And you can use all the guards that we're familiar with function guards. And that's how you can create your requirements for the functions that'll match your trace. And then for the trace, for the function body, we just use return trace, and that gets us the return value as well. Now, once we write this in our shell and we hit enter, we get that same exact match spec that we had 2 slides ago. And you can just copy and paste this from your local machine to the remote one that you're debugging, because it's just a data structure. Okay, let's look at a real world example of doing some reconnaissance with Recon. So for this, we need a little bit of a story. Recently, by now it's probably 6 or so months ago, I upgraded a few services to OTP 24, expecting to get some nice gains from the JIT, right? Not that the work we're doing on these services is particularly computationally intensive, but it's nice to have. And in the meantime, to do that upgrade, I had to upgrade a few other dependencies as well. And it went great. It went great. It was a success on almost all the services until on one service, started to notice a little problem that looks like this. Now, I'm going to break this down on what this graph is. So this graph, the y-axis is % CPU. The x-axis is time. And there's two colored lines. I'm not sure if you can make out the lines, but the purple line is the max CPU across all of the instances of this service. And the blue is the average CPU across all the instances of this service. Now, if you can't distinguish the colors, I'll tell you the purple line, the max CPU, is the one that takes a 90-degree turn and launches into the stratosphere. So what I would notice is this only happened under very high load, but a few instances the CPU usage would go crazy. It would go up to 100% and stay there for a significant amount of time. Eventually it'll come back down, but it never reaches the baseline again. And where you do see it kind of dipping back down, that's where the instance was restarted. And then it pops right back up. And eventually I think we restarted again and it stayed down. Now, what's curious about this is all of these instances are behind a load balancer. Nobody should be doing more work than the others, but some of them were doing a lot more work than the other ones, even after the traffic spike subsided. So when you're faced with a problem like this, what do? Well, we could roll back the change, right? We can go back to OTP 23 and just say, forget it. We could do that and then upgrade one package at a time and see which one caused our problem. But the problem with that approach is this situation only happened at significant traffic spikes, which tend to happen for us this time of year around Sunday night football. Nobody wants to be watching metrics on a Sunday night to see when it goes wrong. And also, it wouldn't necessarily happen every Sunday. So if we downgraded everything and added one package back, how many weeks would we have to go with no problem to be able to say definitively, okay, this one was fine, right? Maybe if the first one we added back, we then see the problem again, then we know. But you have to have so many negative occurrences of it to say like, okay, this package is clear, let's move on to the next one. So rather than that approach, I figure it's all code. We can figure this out. It's a VM. We have these tools to figure out what it's doing. So we should be able to introspect it and figure out what is using the CPU, right? So Recon to the rescue for that. And rather than traces, which we talked about already, we're going to use a couple other tools in Recon to track this down. The first thing we're going to look at are windowed metrics. Recon has this great thing called Recon proc window, and you can give it any metric that you can pull out of process info, such as reductions, message queue length, total heap size. And what it does is it measures every process in the system for that metric, waits however long you tell it, measures again, and then gets the difference between those 2 points in time and shows you the ones that change the most, however many you want. So here's an example. This is from the misbehaving system. So I call Recon proc window. I want to know the reductions, which are, how many operations did this process execute over. I want the top 5 over 10 seconds. Now, a little aside here, you can sort of get some of this information from Observer or Observer CLI, but the problem there is that'll especially for reductions, that'll show you the number of reductions since the process was created. And some processes are long-lived, and of course they'll have high reductions because they've been around for a long time. Other processes may be short-lived, but do a lot of work in that short amount of time. So they might not even show up if you're looking, or they'd be at the very bottom of the list compared to the long-lived processes. The nice thing about proc window is it'll show you over this specific period of time what was the busiest. It might not make as much sense for something like message queue or something like that. You might go to Observer to see what processes currently have the highest message queue. But for reductions, this is super helpful. So what I noticed when I ran this was the top user reductions over this period of time was the logger process. That's kind of curious. Our logger does do a little extra work. We have some sanitization in there to make sure we're not logging database credentials or anything like that. But still, it had, in this time frame of 10 seconds, it had 1.5 million reductions, and the next busiest process was Cowboy, which you'd expect because it's a web server and it's serving web requests at only 600,000. Now there's multiple Cowboy processes, so it's not exactly that logger was doing 3 times the work of Cowboy, but it's still fairly curious that that's the busiest process on the system, right? So I looked a little deeper into this and found that we were logging every 200 level request. This was a pretty easy fix. We added a little bit of functionality to adjust the probabilities that a log will happen. So we can say like all error logs 100% get logged, but maybe success logs, we only log 10% of those, because this is a busy system handling a lot of web requests. So after that, this looks much better. We run recon proc window for 10 seconds, and the highest reduction processes are Cowboy, which is what it should be, right? This is a web server. We're handling web requests. That should be mostly what it's doing with its time. However, this just kind of kicked the can down the road. The problem doesn't happen as much. I think it's because the systems are just not as busy, but it still happens occasionally. So we didn't fix it. In debugging this, I noticed something else that's kind of curious. At the point in time when these errors happened and the CPU would spike, those instances would throw a bunch of these log messages, tried to continue a trace over top of another trace, and tried to finish a trace without an active trace. Now, I know these are emitted by the spandex library, which is a library we use to send traces to Datadog. But they should only happen in like really rare situations. Try to continue a trace over top of another trace means a trace was started, which happens at the beginning of a web request, and then another one was started again before it finished. A process can only handle one request at a time. So that's strange. It's like it's not cleaning up. It's not finishing the trace. And the other one is tried to finish a trace without an active trace. Well, that would only happen if a trace was never started, or a trace was started and then finished again. So this seemed curious to me. And I thought maybe it's not a bug in Elixir and OTP. Maybe it's a bug in Cowboy, because I upgraded Cowboy and Ranch at the same time. And we can use Recon to figure this out. My hypothesis was that Cowboy or the telemetry libraries with it were double emitting events. So it would send it like trace started message, and then it would do it again before it finished. And with Recon, back to tracing, you can trace multiple function calls at once. And you can also, there's some options for IO server and formatter, which we'll look at in a second to see how we diagnose this. So when you're setting up your traces, you have that 3 element tuple again. And I want to see Cowboy telemetry init, Cowboy telemetry terminate, and then Hertz tracer, which is an internal library. I want to see where it starts a trace and finishes a trace. That library just ties telemetry events to spandex to send to Datadog. But what I'm expecting here is I would expect to see Cowboy init, Hertz tracer start, and then Cowboy terminate, and then Hertz tracer finish. I should see init, start, terminate, finish, init, start, terminate, finish over and over and over again. I should never see 2 of those in a row. I should never see that out of order. I'm also going to write a formatter for recon trace. And it just takes a function that takes the specific format of, it's a tuple with the specific format. And this is the format that the Erlang trace function sends its traces as. But to summarize what we're doing here, we're just taking popping a few elements out of that trace and formatting it sort of like a CSV. And then we also open a file. We pass all this to recon trace calls. So we pass it that list of functions we want. We tell it that we want 20,000 traces, and we pass it this IO server option with the file. So rather than dumping those traces that are now formatted to our terminal, we're going to dump it to a file. And then I tell it I want timestamps with my traces, and I give it that formatter function that kind of formats it like a CSV. So once that's done tracing, and I'm going to go over this code really quick because what it does is how it works isn't terribly important, but I'm reading that file back, cleaning it up a little bit, and then I'm grouping all of the traces by PID, because I don't really care what happens between processes here. Each web request comes into one Cowboy process, and then those events should happen in order in that one process. So I group it by process, and then I sort each process by the timestamp. So now I should have a list of all the events that happened per process in order. And then I format it and I dump it out to my terminal. And I see something like this. I get the PID, the timestamp, and the events. And I see init, start, terminate, finish, init, start, terminate, finish, init, start, terminate, finish, over and over and over again. exactly as I supposed it should work, and there's no problems here. This is working as it should. It's possible that in my sampling I missed something, but I did sample a lot of traces, specifically on the boxes that were having issues. And I did this many times and found nothing. So I didn't find my problem here, but I was able to use Recon to dig into the code and see its behavior and rule it out. So unfortunately, this particular thing wasn't a success in finding my issue, but it did give me a lot of information about what the issue is not. So a few other features about Recon that are handy. We have Recon get state and Recon info. These are similar to process info and process.get state, except for they're a little bit safer. I think they trim out some fields that could dump like tons of data to your terminal, and a couple fields that might take a little processing to collect. So they're a little bit safer in that regard. And there's also Recon bin leaks, which is really interesting. What Recon bin leak does is it can find processes holding on to memory that they don't need. And you just call Recon bin leak. And what it does is it collects the number of reference counted binaries in each process in the system. It runs a garbage collection on every process, collects the number of reference counted binaries again, and then compares. So what this tells you is for each process, which ones were hanging onto memory that they didn't need, and we were able to garbage collect. And it shows you the highest offenders of this. And this isn't terribly common of an occurrence, but it can happen if you have, for example, like background workers that deal with large binaries and aren't very busy, so they don't do enough work to use enough memory to trigger a garbage collection. And then they'll just sit there hanging onto this memory they don't need. I think in those situations, if you find that you have one of those, you can tell the process to hibernate, and that'll force a garbage collection. So in conclusion, Recon's great. It's mostly safe unless you're doing something out of the ordinary. For example, when I'm writing to a file, you could potentially fill up your disk on your system, which isn't great. But using it in the kind of recommended way, it's safe, and I find it simple to use. You can keep most of the API in your head. You don't have to have the reference documentation up all the time. And it can give you insights into your production systems that you can't get any other way, because you actually need that production environment with production traffic and production data. And it can help you track down, or in my case, for this particular example, rule out the cause of pesky bugs that only happen in production. Lastly, some resources. I'll leave this slide up for a second in case you can screenshot it or whatever. There's the Recon documentation, which is obviously very handy. There's an article about how to connect to remote Elixir shells that, like I mentioned, we just skipped over that because it can vary so much. And then 2 articles by Kai Wern. I think these articles maybe came out after my talk last year, but these are the articles about tracing and debugging remote systems that I wish I'd written to go along with my talks. So if you like to see this information in more of an article format, I think these are great resources. So that's all I have for today. Thank you for listening.